Hello lovelies, in this video we're going to be looking at atom economy and atom economy calculations for your GCSE chemistry. Now this is very similar to percentage yield, but it is subtly different. Atom economy may seem like a strange term, but in a chemistry sense, all it's referring to is looking at where the atoms go and making sure we don't lose any. Because very similar to the conservation of energy, we have conservation of atoms. In a reaction, the atoms are conserved, they cannot be lost and they cannot be gained from anywhere. Atoms don't just appear and they don't just disappear. Here we have hydrogen in a reversible reaction with nitrogen to give us ammonia. We're going to start this by going through the basics of balancing equations, because this is an important part of atom economy, and if you don't understand it, you'll struggle with the calculations. So hydrogen is H2, nitrogen is N2, and ammonia is NH3. Now with balancing equations, the way that I like you to do it is to draw circles around things. Anything in this circle cannot be changed. Draw a line down the middle or under the equation sign, whether it's an equals or a reversible reaction, and then list simply what we've got. On the left-hand side, we have 2 hydrogens and 2 nitrogens. And on the right-hand side, we have 3 hydrogens and 2 nitrogens. And on the right-hand side, the temptation is to put nitrogen first, but I like to keep them the same on each side. So hydrogens at the top and nitrogens at the bottom. Now we can see this is not balanced. We have more hydrogens on the right than we do on the left. So I'm just going to add in another ammonia, cross out those numbers and redo my numbers. So we now have the same number of nitrogens on each side, but our number of hydrogens are different. The simplest way to add on more hydrogens is to add on hydrogen gas, and we now have 6 hydrogens. So step 1, we've managed to balance the equation. You might get a question that is saying something like, look at the atom economy in the reaction between hydrogen and nitrogen, and the first step would be to write out the balanced equation. Now this is one you might have come across before, so you might be able to remember it, but you would be expected to know the formula of nitrogen, hydrogen and ammonia and be able to balance the equation. Now for this reaction, 100% of the atoms in the reactants on the left hand side end up in the products over on the right hand side. So for this reaction we have 100% atom economy because all of the atoms are used. Let's look at another example which is slightly more complicated. Now we have methane CH4 plus oxygen O2, and this is a combustion reaction, so we will get carbon dioxide CO2 and water H2O. Now I'm going to draw these out for you so you can see that all of the atoms are going to end up in the products. So even if the atoms change their bonds, they change their location, change what they're next to, we are not changing the number of each type of atom. Here in this combustion reaction we are burning things, we're getting 2 gases. You might think that it disappears, but it doesn't. They are still in the equation, they've just turned into different things and might have been lost. So similar to balancing the equation, and I've changed the colours for hydrogen now, corrected those, sorry, you can see that we have 4 hydrogens on the left and 4 hydrogens on the right, and we have 1 carbon and 4 oxygens on each side as well. No atoms have been lost or gained. When you come to do atom economy calculations, you will need to know this equation. That percentage atom economy is the total MR of the required product, and required is important here, over the total MR of the reactants. In this equation, we are mixing zinc metal with hydrochloric acid to give us zinc chloride, the salt, and hydrogen gas. And hydrogen will probably be lost as a gas as it will bubble away. Zinc chloride can be used for a range of different things, but for this example, they might be making zinc chloride for use in a deodorant. So zinc chloride will be the required product. And hydrogen gas would be our waste product. Whenever you see this, whenever you have a question about atom economy, assuming that the equation is balanced, that really should be the first step anytime you see an equation. The first step after that in atom economy is to work out the MR of everything. So the mass of zinc is 65, the mass of hydrogen is 1, the mass of chlorine is 35.5, For hydrochloric acid, we need to add the mass of hydrogen to the mass of chlorine, so that gives us 36.5. And on the left-hand side, we have 2 of those. So we need to times those by 2, giving us a total mass of 73 over the left-hand side. Now moving on to the right-hand side, the mass of zinc is 65, the mass of chlorine is 35.5, and there are 2 of those. Hydrogen has a mass of 1, and there are 2 of those, so that gives us 2 as a total for our waste products. The total mass of chlorine is 71, so 65 plus 71 will give us 136. That is the MR of our required products, that MR of our useful stuff. Now you may wonder why I worked out the MR of hydrogen as well. So the total mass of the product is 138. And this is a great thing you can do in the exam to internally check your maths to be sure that you've got things correct. The total sum of the mass of the reactant, so zinc plus hydrochloric acid, 65 plus 73 is 138. So the mass of the reactants is 138 and the total mass of the products is 138, showing us that we've done our sums correctly. Even though we didn't need to do that sum, it's giving us a little bit of reassurance in the exam that we've done things properly. The next step, after you've worked out all of the masses, is to pop it into the equation. So 136 is the total MR of the required product, divided by 138, which is the total MR of the sum of the reactants. And your calculator will show a decimal for this. But we are looking for a percentage, so you need to times that number by 100. A sensible number to round it to is 1 decimal place, unless the exam tells you something different. If the exam says to a whole number or 2 decimal places or a number of significant figures, please do that. And this is a percentage. Here is another example where we're going to be adding an acid to an alkali and getting a salt plus water. So we're adding hydrochloric acid to sodium hydroxide to give us sodium chloride plus water. Hydrogen has a mass of 1. Chlorine has a mass of 35.5, giving us an MR for hydrochloric acid of 36.5. Sodium has a mass of 23. Oxygen has a mass of 16, and hydrogen has a mass of 1. We can add all of those together to get the mass, the MR of sodium hydroxide, which gives us 40. The total MR of all of the reactants is 36.5 plus 40, giving us 76.5. We can now move over to the right-hand side and do exactly the same with the products. So sodium is 23 and chlorine is 35.5, giving us the total for sodium chloride of 58.5. Now I'm going to work out water as well, so we can do our internal check. Hydrogen is 1, there are 2 of them, 1 times 2 is 2. Oxygen is 16, add those together, we get 18. Now hopefully, assuming we've done our maths correctly, 58.5 plus 18 should equal 76.5, so that we know we have the same on either side and we haven't lost anything. We can now put the numbers into the equation. The mass of the required product is 58.5 and the MR of all of the reactants is 76.5. Your calculator will again give you a decimal, but we need to times it by 100 to get that percentage, giving us 76.5 as our percentage atom economy. You might see some exam questions talking about green or sustainable chemistry. Now, this might be a slightly harder exam question, but there's nothing in here that you actually can't do. If we look at this equation for the electrolysis of water, we have water being turned into hydrogen gas and into oxygen gas. Following exactly the same process as before to work out the mass of everything, if oxygen is the required product, giving us an atom economy of 89%. If hydrogen is the required product, then our atom economy is much lower at just 11%. However, both hydrogen and oxygen are useful gases. What if, in an effort to make this equation more sustainable, in an effort to make this reaction more green, better for the environment, what if we found a use for the waste product? And then both the hydrogen gas and the oxygen gas would be the required product from this reaction, and the atom economy for this would be 100%. There would be no waste. This is much better for the environment, this is much greener. This atom economy is much better. There are two main ways you can improve the atom economy of the equation. The first one that we went over in the other slide is that we need to find a use for the waste product. If they are no longer waste products and they are required and useful products, the atom economy will improve. The other thing you can do is to find an alternative pathway for making your required product so that the atom economy improves. Now, if you think about this in an overall sense, just because the atom economy has improved doesn't mean this equation is better for the environment, doesn't mean it's more green in a chemistry sense. Just because the atom economy might be higher, that doesn't mean it's better because it might have higher energy usage, it might have higher electricity usage, and there are lots of things to think about when we are linking things together in green or sustainable chemistry.
Ouch! This is why in some videos I have unexplained scratches.